So let me just start sharing just a minute. Hi, uh, sorry for starting late. I was stuck in some other meeting. Okay, so let's start. Welcome to week 9 session of Semiconductor Device Modeling and Simulation NPTEL course. I am Om Maheshwari, and today we will discuss some questions that will help you in your assignments as well as your exams. Okay, so in this week mainly we will be focusing on uh, the generation and recombination models. We will see different kinds of generation and recombination models and see what is their effect in the devices. So before starting with the questions, this is just an overview and a snapshot that I've taken uh, from the video lectures. So this summarizes very well what different mechanisms we are dealing with. So the generation recombination mechanisms can be classified into two sections. First is a two-particle interaction, another is a three-particle interaction. In two-particle interaction, we basically further classify based on the energy band gap of the semiconductor. One is direct band gap, another is indirect band gap. In direct band gap, we can have uh, photogeneration, that is generation of photons. Radiative recombination is again, it radiates uh, some energy in form of light. So both of these are emit photons. And thermal, uh, okay, so photogeneration is actually when light falls on it, it generates electron hole pairs. Radiative recombination is when electron hole pair combine, they generate photon. Similarly, the direct recombination generation can be thermal also, where on giving some thermal energy, the electron hole pairs can be generated, or when electron hole pairs recombine, they generate some thermal energy. In an indirect band gap semiconductor, all this happens in two steps. Uh, due to the assisted which could be assisted by traps. So trap states in the between the band gap can help can act as an intermediate point where electrons and holes can come and recombine. Another is the surface generation recombination, where if there is an interface where the semiconductor material is terminating, generally there are a lot of dangling bonds which creates a lot of surface states which acts as sites for generation and recombination processes. In the three particle system, what usually happens is some particles, uh, three particles are involved in generation recombination, out of which two may have been generated or recombined, and due to the action of the third particle. And impact transition is a is an example of this, where very high speed excited electrons strike on the lattice to generate more electron and hole pairs. And the opposite of this is Auger recombination, where in Auger recombination what happens is when two particles are, let's say an electron and hole are recombining, so they generate some energy which is transferred to some third electron, which increases its kinetic energy. So this is like quite opposite of impact ionization, that is Auger recombination. Okay, so now let's start with the questions, and we will see more concepts as we go through the questions. So the first question is, in case of band-to-band recombination, how increasing doping concentration affects the carrier lifetime for low-level injection? No, it's D, decrease the carrier lifetime. So okay. Always in recombination, you remember one thing: if carriers are more, there will be more possibilities of uh, recombining, right? So if uh, be it in any kind of recombination generation process, if there are more carriers, there's more probability of recombination. So if we are increasing the doping concentration, we are increasing the concentration of one of the carriers at least. Let's say if it's a p-type semiconductor, we are increasing Na, that is, we are increasing the whole concentration. So whatever electron minority electrons it has, they have now more probability of combining with the holes, as because simply because there are a lot more holes now to recombine with. So for any, this is a general statement for any kind of recombination, be it band to band or Auger or any other kind of recombination or generation process, doping will always increase the recombination, and if recombination is increasing, that means your carrier lifetime is decreasing. Or recombination rate simply is 1 by carrier lifetime, right? Okay, so this is decrease in carrier lifetime, and if we go through the videos, the same thing is explained for band, specifically for band to band recombination. So this is a general expression for the recombination is some alpha factor times np minus ni square, which is actually the change in, due to recombination or generation processes, whatever is the change in the equilibrium concentration of n and p, is that delta n by tau. And under low level injection approximation, we ignore some of these terms to simplify it, and what we get is finally this 1 by tau is alpha r times Na. And here we can directly see the uh, carrier lifetime is inversely proportional to Na. So if Na will increase, carrier lifetime will decrease. It's just tau. I hope this is clear. Yeah. Yes. Alpha you can, yeah, yeah. Alpha uh, is like, you can say, a proportionality constant here. It is just a relational parameter between the rate. It is a constant parameter. Yeah. So 1 by tau is proportional to Na. So that means tau is inversely proportional to Na, and the alpha is just a proportionality constant. Yes. The carriers that you are that are generating or recombining are less than the existing doping. That is the low level injection condition. For high level, this is the opposite. Whatever you are generating or recombining is much greater than the existing doping. For that case, Na will not matter because now what you are generating is much greater than Na itself. So then Na, it is kind of independent of Na, as you can see uh, here, right? It is now independent. Uh, Delta, I think this delta N or delta P, whatever you are recombining or generating, they have generalized it. Instead of saying N or P, it is representative of whatever you are generating, the number delta N or delta P, generated or recombined. Yeah. R, this, yeah, yeah, yes, yes. What? This, what is the question? Sorry, this, yeah. Yeah. Okay. So let's move on to the next one then. Question Next question is, which recombination mechanism involves the combination of an electron and a hole bound together? No, this is something different from our recombination. It is exciton. So yeah, okay. No, exciton is something different. So let me explain. So excitons, what are excitons? Excitons are coupled electron hole pair. That means due to some forces in a semiconductor, you have electrons and holes which are like very near to each other, but they have not recombined yet. And so this electron hole pair itself is called as exciton, and it, as you can see in the diagram, it moves as a unit in response to applied forces. So if you apply some, let's say some potential or some bias, whatever you apply, these two move together because they have some attractive force in between, which binds them together. And uh, it so the important thing, another important thing here, it gives rise to subband gap radiation, usually at low temperatures. So what this means is, even if you have a direct band gap semiconductor, and in the direct band gap semiconductor there is this electron hole, this exciton pair, which has to recombine. So what we have seen in the theory till now is, when an electron will recombine with a hole in the valence band, it will, in the direct band gap semiconductor, it will emit some photon, right? But But here what will happen is these are these have the whatever when they recombine, very less energy is emitted, which is uh, which is much lesser uh, than the photon energy. So it leads to uh, uh, the radiation it emits is thermal when they recombine. So here subband gap radiation is mainly referring to that part. Yeah. Yes. Yes. Not. Yes. 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 Photons. Yeah. Yeah. Lattice vibration is photons. Yeah. Yes. Light is photon. Yes. Yes. Uh, okay. So I do not know the exact physics of this, how excitons generated. So, but yeah. No, no. So what they're saying, it is like a drawback of that. Like we want it to be only photons. We want the recombination to always give us photons. But if we operate these LEDs at low temperatures, what happens is they tend to, instead of generating, they emit lesser light. That's what they're trying to say here. Like we want it to always give light, but due to this presence of excitons at low temperatures, it will start to give some thermal generation, and the light emitted will be lesser. That's what they're trying to say here. Yeah. Mm. Okay. Okay. Uh, could be true. Like I cannot comment on that. I do not have that uh, clarity on that right now, unfortunately. I do not know how organic solar cells work. But yes, 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 yeah, yes, yes. They are excitons. Yeah. The combination of this electron and hole is called exciton. Okay, so this just tells you in energy space, like let's say this is kind of band diagram only. This is E versus X, you can say, and this is like maybe this is the real space. This is X and Y. So they are saying like the electron or hole can be far apart in the energy space, but in real space they can be very close to each other. So they are saying that in an energy space, it may be possible that electron and hole pair are separated by some energy. They have different energies. But if you see in the real space, that is in our 3D world in XYZ dimensions, when we are not in the position space, when we are not considered with the energy, we can say those two different particles with different energy can be very close together. Yeah. In space, they can be very close together, but this particle may have different a high energy. This particle may have a different low energy. Okay, so our question was which recombination mechanism involves combination of electron and hole bound together? So basically, electron and hole bound together are excitons. So this bound together keyword is important here. And if they are excitons, it will go through exciton recombination. Okay, see the next one. Okay, the question is X. Yeah. So as I said, we expect it to, if there is the band gap energy, it should have emitted a photon, but it does not emit photon. It emits much lesser energy in form of thermal energy. So why is that happening? That is the question. No, it is actually C. Since they are bound together in a space, we have to, before recombining them, uh, we need to overcome whatever energy is there to which has bounded them close to each other, so that then only recombination can occur. So whatever is the force that is binding them together, that has to be overcome to make them free. Once they are free, then only we can recombine them with each other. Okay, next question. Which of the following recombine? Yeah, 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 yeah. So SRH recombination is trap assisted, and I think I have a slide for SRH also. Yeah. So these are just different mechanisms that can be there between a trap and an electron or hole. Either an electron from the conduction band come to the trap state, which is called electron capture. An electron from the trap state can go to the conduction band, it is called electron emission. A hole from the valence band can go to the trap state, it is called hole capture. And a hole from the trap state can come to the valence band, this is called hole emission. And if you see, they have also, for this they have represented two forms, because if what I'm saying is a hole is going to the trap state, we can also say that an electron is coming from here to recombine with this hole. Both of these mean the same thing. Electron emission is yeah, you can say that, but electron emission here they are referring to only when the electron goes to the conduction band. Yeah. Mhm. Uh, I think the naming convention is such that uh, electron emission is only for something when electron goes from trap state to conduction band. Both of these things, since they are equivalent, either a hole is going to the trap state or an electron is coming from trap state to valence band. That both are, yes, because both result in loss of this hole from the valence band. And the similar thing is in hole emission, where either a hole comes from here or an electron goes from here to leave a hole. In both the cases, a hole is generated here. Both of those are called hole emission. Okay, so the question was, which of the following are trap assisted, and answer is SRH. Okay. Next question is, calculate the SRH recombination rate of an uh, N-type semiconductor with excess hole concentration of 10 to power 19 per meter cube and minority lifetime of 2 microseconds. So in the interest of time, I'll just go explain the formula from the slides. So this is actually a this derivation is given in the video, how we get this very long expression of R. Basically, this is simply again NP minus NI square. This will always come whenever there is a talk of recombination and generation. And here N is N0 plus delta N, and P is P0 plus delta P, and minus NI square. So this difference in the equilibrium, we know NP is NI square in equilibrium. And when there is some disturbance or perturbation, this NP is no longer equal to NI square. So whatever is excess is generated or recombined, we find from by subtracting this NP minus NI square. So this will always be there when we talk about recombination or generation. Now, with this assumption of low level injection or high level injection, we just simplify uh, this equation to neglect those terms which are not important for us. And when we do that here, we get R equals to, in low level injection field, delta N by tau N or delta P by tau P. This is the recombination rate in case of low level injection. In high level injection case, this is delta P upon tau P plus tau N. Yes. Until unless it is mentioned that it is high level, we will always assume it to be low level. High level injection is very extreme case which normally does not happen. Low level injection is the generic case which always happens in the semiconductors. Yeah. Yes, yes, yes. That's true. Yeah. Okay. So uh, yeah, it is del P by tau P. This is 10 to the power 19 per meter cube, and the lifetime is 2 microseconds. So we need to convert it into some units that are there. We also okay. So this is 10 to the power 19 into divided by 2 into 10 to the power minus 6 micro. This will be seconds. This is per meter. Now, if you see, I will get a number which is much larger than 10 to the power 19, right? It will be 0.5 into 10 to the power 25, right? But I see all the answers are in this 10 to the power 19 range. So I need to change this. Either answer is in meter cube or in centimeter cube. So I need to change this unit. So to do that, yeah, it will be 10 to the power if I. So I can change 1 meter cube is 10 to the power 6 centimeter cube. So this 10 to the power minus 6 will cancel and I will get 0.5 into 10 to the power 19 centimeter cube per second. This is the final answer, which is option C. So you need to be careful with the units in your exam. They are important here. Okay, so next question, I think let's check this one first. This is again a similar question, just with different numbers. We again have to find R. Yeah, 10 to the power 15 into 10 to the power minus 6, if I say per centimeter cube, and 1 microsecond is 1 into 10 to the power minus 6 seconds. So this will cancel and I will get 10 to the power 15 per centimeter cube per second. This is option B. Okay, so let's check this question now. Yeah, sure. Okay, so let's take this question. Under high level injection, right, this we have just seen now. It is delta P upon tau P plus tau. Okay. Uh, okay. Next question. Given an n-type semiconductor material with capture coefficient of 10 to the power 14, 10 to the power minus 14 meter cube per second and a trap density of 10 to the power 14 per centimeter cube, determine the minority carrier lifetime in the material. So for this, we need to know the relationship between capture coefficient, this is Cp, trap density Nt, and the minority carrier lifetime tau p. And if I go back to the lectures, this relationship is given like this. In steady state, this is again from the derivation of SRS recombination. I have taken this snapshot. So that is the trap assisted recombination. So how this minority carrier lifetime is related with the concentration of the traps. The Cn is just, you can say, a parameter which does not have much significance, physical significance, but these two are the real parameters. Tau n is the minority carrier lifetime and T is the concentration of traps in the semiconductor. So how these two have an inverse relation, and so as we saw, we can write tau p is 1 by Cp into Nt. So now if we solve this, Cp is 10 to the power minus 14 per meter cube. 1 by 20 watt. Okay, yeah, that's correct. So let me solve this. Into Nt is 2 into 10 to the power 14 per centimeter cube. Now would like to like balance these units in centimeter and meter cube. So I'll convert this to centimeter cube. I can write this as 10 to power minus 14 into 10 to power 6 centimeter cube. Now this 10 to power 14 and 10 to minus 14 can cancel, and this will give me centimeter cube, and per centimeter cube will also cancel. What this would give me is 0.5 into 10 to power minus 6 second, which is 0.5 microsecond. Stop. This is option A. All right. Okay. So let's see the next question. Calculate the absorption coefficient alpha of a semiconductor if a 2 millimeter thick semiconductor reduces the intensity to 0.1. Okay, so this question is actually based on the how we actually physically characterize the recombination or generation. So this is given in the lectures, I think in the second lecture of this week. So this is basically what we do is, in a semiconductor piece, between some length delta x, we see the change in current when we shine some light or something to do the recombination or generation, right? So this basically, if we had I naught current going here we get some current which is some alpha x times I0 I naught, and if we subtract that, if we subtract these two, I naught minus alpha x I naught, we get the change in the current, and that we can write in the differential equation form: delta I by dx is minus alpha times I, and the solution to this differential equation is this: I of x is I0 e to the power minus alpha x. So we will use this equation to determine. Yeah. Yeah. Yes. Actually, it is dx times I naught. This is the distance. It is like alpha is some factor times dx I naught. It is dependent on the length that it is passing. So this current I may rewrite this IF is alpha is some factor into dx times I0. Here it is input is I0. Yes. Yeah, equal to some the basically this difference will come because of whatever process we are doing. Either we are uh, heating it up or we are applying photons or something to generate these two, that will actually bring the change in this current. So there is some external generation or recombination mechanism going on. So this delta current delta I is representative of that generation or recombination process, because you applied electrically, you applied I0, but you are getting something else now, which is only possible when there is some external process happening that is changing this current. Else if you apply I naught, always output should always be I naught only. So yeah. Yes. I naught minus alpha dx I naught. is I. If I take, I think, if I take I not common, it can end 1 minus alpha dx I. Okay, this derivation I'm not sure. You can see in the video how I think the professor has shown how to solve this. Uh, but anyways, it is not important. The derivation is not important for us here. Yes, this is the expression and this is the solution to it of this partial differential equation. Yes. What? Sorry. Mm. Yeah. 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 I think this is done here. Yeah. I think that is what is done here. It's not clear in the screenshot, but something like this. Yeah. Okay. So basically, we will be using this expression for this as option question. So question asked is calculate this alpha. If dx is given to us or x is given to us, x is given, alpha we have to find, and I by I naught is given 0.1. And so the negative. Okay. So this is option C. Okay. So see the next question. Given uniform illumination with light resulting in an optical generation rate of 10 to the power 20 per centimeter cube per second in a p-type semiconductor. What is the distance between electron quasi-Fermi level and intrinsic level? Assume intrinsic carrier concentration is this, tau 1 is this, and kT is 26 millivolt. Okay, so a lot of things are given in this question. First, let's mark these. There's some generation rate given. G is 10 to the power 20 per centimeter cube per second. We have P type semiconductor. We have to find difference between EF and EI. To find EF minus EI, and intensity carrier concentration Ni is given. Tau n is given is 1 microsecond, and Kt is 26 millielectron. Okay, so okay. So the generation rate is 10 to the power 20 per centimeter cube per second, right? And we have to find EFN minus EI. It is a P-type semiconductor. So in P-type semiconductor, majority is already holes, right? This is EI, this is EF. And due to some doping, Na is responsible for the position of this EF. Now what it is, the question says you are shining some light on it, which is causing the optical generation, which is generating electron hole pairs, right? And in and those electron hole pairs are such that it will generate more holes here, such that this EF may or come even closer to it, and it is generating, since it generates electron hole pairs, electrons are also getting generated. So there are some electrons that have been thermally generated, due to which we can find the position of the EFN, the quasi Fermi level EFN, that will signify what is the minority carrier concentration of the electrons in this semiconductor. So in the absence of light, we would not have had this EFN, because there was no external force that would have changed the uh, uh, electron concentration, and the only thing responsible would have been this background doping. But now, since we are generating due to light, there is some other factor which is generating holes, or which is generating electrons and holes, and since electrons were in the minority earlier, now uh, they, uh, their concentration is changing. That is what is signified by the quasi-Fermi level EFN. So the question basically says to find the difference between this EFN and EA. So whenever we have to find the energy difference between two levels, what we do is KT by Q ln. Okay, it is not Q since it is not a voltage. It is KT ln whatever signified by this, that there will be delta n that are generated by EI, which will represent Ni. So like EF minus EI, how we find it is KT by Q ln Na by Ni, right? Ln Na by Ni. This is EF minus EI. Similar to that, uh, EI minus EF, since it is P type. Similar to that, here we have EFN. For that, we have delta n, that has the excess generated carriers due to sorry, it will be Na, right? Y and D. EF is this, right? It is due to the acceptor dopants. This is cementous P type. Y and D. And D, Y and D will be no cementous P type, right? The electrons are generated are the minority carriers due to light, right? That is what we are measuring here. So EFN and EF are different things. Yes, yes. Okay, so in this question, this is the okay. This is what we will be use. We have to find EFN minus EI. KT we know, Ni we know, what we know is don't know is delta n, how much electrons are generated due to light. So to find that, uh, delta n we can write as generation rate into the generation time, tau n. So delta n will be, generation rate is 10 to the power 20 per centimeter square per second, per centimeter cube per second, and tau n is 1 microsecond into 1 into 10 to the power minus 6 second. These two will cancel, and this will give me 10 to the power 40 per centimeter cube. Okay, so we have EFN minus EI equals to KT ln delta n by Ni, which is 0.026 ln 10 to the power 14 by 10 to the power 10. So solve this. It will be 0.239 approx or 0.24. Yeah, or 0.24 if we can say that. So answer will be option C, 0.24 electron volt. Okay, is this clear? Can we go to the next one? Okay. Next question is, in a heavily doped N-type semiconductor under high level injection, which recombination mechanism is likely to dominate? Why? Mhm. So high level or low level injection can take place in any of the recombination injection condition, right? High level, low level just depends on the background doping. Either it is higher or lower. Uh, so high level, low level, how you define whatever you are generating, delta P or delta N, is it larger than the background doping or not? That is what it will determine it is high level or low level or not. So this is the low level condition. Opposite is the high level condition. And delta P is much greater than Na. Now the question is not actually about high level or low level. Question is about uh, the different types of recombination. Okay, so which recombination is more prominent when there are more number of carriers? So actually, as I said, like all of them would increase when I increase NA, that we saw in the first question itself. We saw the band to band and all that. But there is some particular types of recombination that are more prominent. Let's say in a semiconductor where there is a lot of doping, maybe there is one of these which will happen more than the other. Maybe, as you said, SRH is more than radiative or something like that. That we have to conclude. Like within this semiconductor, which recombination will is like more likely to. And why do you think that? Mhm. Does it have anything to do with doping? So actually, if you remember, uh, we saw certain type of recombination when we were seeing this. Okay, so if you talk about Auger recombination, it is a three particle system, three particle interaction. So when there are more number of particles, it is more likely that Auger will happen. So the answer to this is where were we? Right. Auger recombination is more likely to happen when there are more number of carriers, since it involves multiple particle. It is a multiple particle interaction. Yeah, high level injection is not the key here. All can give you high level uh, injection condition, but the key here is the dependence of doping and the recombination mechanism. Okay, so as it says, the uh, there's collision between two like carriers. Now, basically, what high level injection means, right? When you have a lot of uh, uh, electrons are there, right? And since there are a lot of electrons, they are more likely to collide with each other, to transfer their energy with each other, and at the same time recombine with the holes. So this is basically the three particle interactions would be more. Since there is high level injection, there are more such electrons, and the doping is also high. That means uh, there are more holes present which to recombine with it. Does it make sense? Okay. Yeah. So basically, what is happening, you can say, is a more easier way to understand this is right. But that is true for all the recombination generation. I'm saying specifically why Auger is the answer to this question is uh, yes. If I so what they're saying is they have a heavily doped N-type semiconductor, right? So this is an N-type semiconductor. Let's say we have a PN junction, okay. And here we are seeing what is happening or not. So when we apply, let's say, a forward bias to it, what will happen? Holes will go from here to here, electrons will go from here to here. Right. Now let's say you apply so high bias, let's say you apply a very high bias, such that a lot of holes are going from here to here, and your doping here is NT. So there are already a lot of electrons here. Now this is the high level injection of holes here. So a lot of holes are there which have been injected, which can collide with each other and transfer energy. And since the doping is also high here, these lot of holes can combine with lot of electrons. So that's why uh, the condition favors Auger recombination, because due to high level injection, there can be a lot of more collisions here, and since the doping is also high, then the these large high level injected high injected you can say carriers can uh, recombine with the uh, electrons in the that have been doped. Okay, so to summarize, the key here is Auger recombination is like more dominant when doping is higher. That is the key takeaway from this. So this, just you need to remember this. All right, so next question is this is okay. What are the units of Auger coefficient Cn and Cp? Now first we need to see what are Auger coefficients. So this is how the Auger recombination is defined. They are just again some coefficients Cn and Cp here. So this is a three particle process. In earlier recombination case, we see only this was the dominant term, Np minus Ni square. Now, since it's a three particle system, there is one more this carrier term, which is N times Cn or P times Cp. So now it is actually a three particle system. These two may recombine and this one will exchange the energy. Yeah. So right. So this is written here also. I think 10 to the power 6 centimeter to the power 6 per second. So this is option B. Okay, next question. Which of the following is an inverse process of Auger recombination? Right. Right. It is impact dimension. This we saw in the starting also. Yeah, when I was explaining here. Impact dimension is when a very excited particle strikes to the lattice to generate electron and hole pair. Right? And Auger is something different when electron and hole recombine and the energy generated is taken by another like carrier which which gets excited with this generated energy. So both of these are opposite to each other. Okay. So next question. Which energy is emitted during radiative recombination in indirect bandgap semiconductor offer lower than the bandgap energy? No, effective mass is uh, uh, we cannot say if it is an indirect bandgap semiconductor, it will have higher effective mass. Effective mass is due to the curvature of the EK diagram, right? Okay, so let's say two cases. This is direct bandgap. This is okay. This is indirect bandgap, right? Both of these can have the same curvature. Both of these conduction bands can have same curvature, and definitely will have yeah, they can have the same M star. So this option is not correct. Effective mass does not have anything to do with this. We cannot say indirect band gap has higher effective mass. This is a wrong statement. Okay, so the answer is due to the phonon involvement in the recombination process. So Basically what, yes. So if you look at this, so how the indirect band gap emitters recombine. So they need to change their momentum as well as their energy, right? So to change the momentum, they interact with the phonons, which change their K value. So to go from this K state to this K state, they interact with the phonons, and here they emit the energy. Once they are at the same uh, K value, they emit the energy here. So this, I think this kind of question we have seen before also. So this is due to phonon involvement in the recombination process. Okay, so I think this is a repeated question. What is the primary difference between radiative recombination of free carriers and exciton recombination in terms of emitted photon energy? Uh, no, no, we saw this, right? They emit lesser energy because some energy is required to separate to overcome the binding energy, right? Right. So they emit on recombination, they emit lesser energy. So it should be option B. Okay. So uh, this is repeated. What is the inverse of Auger? It is impact annihilation. This question is also similar to what we have already done, so I'm not going to solve it. I think we saw tau t is 1 by Cp times Nt. So with this you can solve this one. So just calculation. Okay. Were the values same? Just check that. Yeah, 0.5 microsecond. And this is the last question I have for today. Again, yeah, but I think the value is different now. It was earlier 0.1. This one is 0.15. So the logic is same. I by I naught. It is 0.15 is e to the power minus alpha x. So we can say ln 0.15 is minus alpha x is 2 millimeter. So alpha is minus ln 0.15 by minus 2 millimeter. So okay, and when we divide it by 2, what we'll get? Okay, 0.948 per millimeter is closer to, I think, 0.95, option C. Okay, so I think these are all the questions I had for today. And we saw a lot of concepts also this time. Okay, so I think we can close the session for today. We can meet in the next class. If you have any doubts, please feel free to reach out to me on my email. Uh, I will upload the recording and as well as the this lecture notes on the sheet that is shared with you. So thank you for joining. Let us meet next week. Yeah, sure, no issues. Sure.